Today we're going to talk about optimal aircraft rerouting during commercial space launches. And while many of you might not know that this is a concern, it's actually been growing and has a lot of attention in the media. For instance, at the end of last year, the Washington Post had this article, Companies in the Cosmos, Gridlock in the Sky. And what it talks about is how more and more space launches are occurring, and that means that more aircraft need to be rerouted on a more frequent basis. Earlier this year, The Verge posted this article about commercial spaceflight growing and how it's starting to impact aviation. And in this article, they specifically talk about how many different entities have gone ahead and gone to the Senate to push that the FAA changes the current procedures during space launches because they find them inefficient and antiquated. Also, the Airline Pilots Association published last year this white paper. In this white paper, they talk about some of the challenges that the aviation industry is having with more space launches. And they actually go through and break down some of the costs that are associated with each space launch. So we're going to go through that now. For instance, actually, let me move the mouse. Perfect. For instance, a SpaceX Falcon Heavy launch in February of 2018 caused 563 flights to be rerouted. Each rerouted flight had on average an 8-minute delay and a 62 nautical mile flight deviation. In total, this is about $550 per flight that was rerouted, costing airlines over $300,000. For some reference, $300,000 is about 3% of United's daily profit. So that's just one airline, and there's multiple in the airspace. And that might not seem like a big deal if you're looking at a launch once every few weeks or once a month. But if you start to have a launch multiple times a week or even multiple times a day, this starts to add up. And so that's looking to be more of a reality. So as we have space, people's interest in space is growing, and we have companies working on suborbital reusable vehicles that could launch multiple times a day. This could become a growing concern. And on top of that, right now, most of the launches are done in more remote or oceanic areas, and people are looking to have launches in more populated and airspace dense regions. For instance, they're looking to put a spaceport right outside of the Denver airport, and that means that you wouldn't just be rerouting a few flights, but drastically more flights per launch. And so you might be wondering what's causing all of these delays and this additional cost. And so every time there's a launch, the FAA is going to shut down a large column of airspace for a long period of time. This airspace is going to be restricted for hours before the flight or the launch, during the launch, and even sometimes hours after the launch. And this is going to be a static region that doesn't change. And so if you look at the picture on the left, what you see is a temporary flight restriction, or TFR, off the coast of Cape Canaveral. And this is just the TFR that's going to affect the domestic airlines. And in the middle, you see it projected on the coast of Cape Canaveral. And on the right, you can see some of the flight paths that would fly through that region or potentially need to be rerouted because of that region. So what we're looking to do is reduce airspace disruptions while maintaining airspace safety. And so today's talk, I'm going to talk to you about how I've done that. So how I've formulated the problem as a Markov decision process, how I've formulated it for 2 different action spaces, the different MDP solution techniques that I solve it with, the actual solutions that I find, and the results they provide in simulation. And so the first thing we're going to talk about is the MDP framework that I use, and to begin with, why I choose an MDP. And so the first thing to remember is what the actual problem is. So we want to address an increase of airspace disruptions while minimizing airline cost. And the general solution is to move from those static prohibited regions to something that's more dynamic. In the past, both at Stanford and at the FAA, research has looked into probabilistic risk analysis approaches. And what they do is find the probability of pieces of debris being in certain sections of the airspace and actually defining restricted regions around them through either compact envelopes or space transition corridors. But instead, what I'm looking to do is to help develop the framework for something that could be used for a decision support tool. So something that the FAA is familiar with is using decision support tools during anomalous events, such as severe weather or large sporting events, to help guide them on how to reroute aircraft in real time. And so what I want to do is provide a solution that can give air traffic controllers the rerouting commands that they need to provide to the airplanes. And so that means that my MDP my framework has to follow a few criteria. So to begin with, it needs to provide actions as its solutions because that's what we want to provide to the air traffic controllers. It needs to be able to model a sequential problem that has a lot of stochasticity. We're dealing with a problem that has a lot of inherent uncertainty. Will an anomaly or an explosion occur? Where will potential pieces of debris fall? And so we need something that's going to handle that. It needs to have a fast solution in real time if we want air traffic controllers to actually use this. So we have two options. Either it can be solved completely offline and queried fast in real time, or it can be solved online but very quickly. It needs to be proved for safety critical systems, and it needs to be able to undergo the FAA approval process and adoption process. So the selected model is a Markov decision process. A Markov decision process, or MDP, is well known for being able to model sequential problems with a lot of uncertainty, and it's able to be solved offline and queried quickly in real time. And due to the creation of ACAS-X, which is a manned collision avoidance system that is getting put on all commercial airlines today, we know that the FAA has dealt with systems like this that use MDPs as their baseline framework for moving forward. So a little bit more about an MDP. What is it? So it's actually using four different parameters to model your problem. So a state space, action space, reward function, and transition function. For instance, if we look at the model on the right, the green circles 1, 2, and 3 represent your states. And from each state, you can take one of two of the squared actions, A or B. For instance, if we're in state 2 and we take action A, 60% of the time we'll transition into state 1, and 40% of the time we'll transition back into state 2. So those black numbers represent your transition function. If you're in state 2 and you take action A and you transition to state 1, you get a +1 reward. And so those little orange arrows are your rewards. And this can be expanded for the rerouting aircraft problem. For instance, if we were to say that 2 is currently a state where you're on a collision course towards a piece of debris, if you take action A, 60% of the time you land in state 1, which is now free of debris, so you get a +1 reward. But if the pilot didn't respond, maybe you stay on a collision course towards a piece of debris in state 2. In order to build my MDP framework, I have to set up a scenario that I'm going to model. So the scenario I'm going to explain here is what my solutions and results are based off of, but the underlying framework can be used with any of these components. Can all be plug and play with different components based off of the launch you're looking at. So I investigate aircraft at 35,000 feet, and I model a 2-stage to launch orbit or rocket out of Cape Canaveral. I model the debris using the Columbia Disaster Debris Catalog, and I use Stanford's Range Safety Assessment tool to propagate where potential pieces of debris and what their trajectories will be. And everything is solved in an east-north-up coordinate frame out of Cape Canaveral, or centralized at Cape Canaveral. Overall, my MDP framework state space is going to model where an aircraft is and where potential pieces of debris are if there has been an anomaly. So if we look at the bottom right image, what you see is the actual debris from the Columbia disaster. And what they did was take all of the debris and bin it into 11 different categories. The categories are going to be based on ballistic coefficient, weight, size, coefficient of lift and drag, and they're going to represent the different types of debris that could be falling through the airspace. If you look at the top right, you're going to see for one time of anomaly where one piece from each of those bins would fall. And the bottom left is going to be for multiple times of anomaly where one piece from one bin would potentially fall. The action space we're going to look at is twofold. So the first one we're going to look at is heading changes. So for instance, during weather events, aircraft are rerouted by giving often rerouted by giving heading commands to turn right or left around severe weather systems. We're also going to look at metering actions or speed changes. So when you're looking at oceanic flights, you're no longer getting those quick and real-time heading changes, but instead they're told times to be at specific metering points. So in this image, you see a bunch of little blue diamonds, and those blue diamonds are waypoints that aircraft have to hit at a specific time. And so by changing the speed, you can change when they hit those waypoints. Our reward function is going to look at both a safety and an efficiency reward, but you also don't want to reroute aircraft unnecessarily. And our transition function is going to model the pilot response rate, the aircraft's capabilities and dynamics, the launch vehicle status, and potential pieces of debris information. So we're going to go a little bit more in depth on our on my heading formulation. So the heading formulation is going to be a 5-dimensional discretized grid where the Three initial parameters are going to be the east position, north position, and heading. So if you look at the middle image, you see an east-north grid where an aircraft can be located anywhere within that grid and can have a variety of different headings. And then we use time of anomaly and time since launch to query where potential pieces of debris will be. So if you look on the right, now there are pieces of debris that we've been able to determine based off of the time. The action space is going to either be no advisory or a strong right and left turn, a weak right and left turn, or straight. The strong right and left turns correspond to a standard rate turn, and the weak right and left turns correspond to a half standard rate turn. And we have a no advisory command because we don't assume we know the path of the aircraft, just the position of the aircraft. The reward function is going to be a lambda value times an efficiency reward plus a safety reward, and lambda is going to be determined experimentally. The actual efficiency reward is going to be based off of the strength of the action. So the stronger or the larger the stronger the negative reward, for the stronger the action. And the safety reward is going to be based off of a distance away from a threshold. The transition function is going to update an aircraft position using the heading and velocity. And the heading is going to be updated based off of the commanded heading. We're going to assume that a pilot responds 50% of the time, which means on average a 20-second response rate. And if the aircraft is commanded nil or no action rather, it's going to follow a normal distribution. The reason that we have it follow a normal distribution is again because we don't know the path of the aircraft, just where the aircraft is. So inherently the aircraft could be turning or could be going straight. The time of anomaly is only updated once, and it's updated to have an anomaly 50% of the time during the first stage of launch. And we're going to update the time in 10-second intervals. So everything is solved in 10-second intervals. So every action an action can be commanded every 10 seconds. And for this formulation, we're only going to be looking at domestic flights. So we only consider debris that will fall through the airspace within 10 minutes of an anomaly. So now a little bit more about the metering formulation. So the metering formulation, again, is going to be used during oceanic flights when aircraft are flying specific paths of waypoints. So now we actually know the path of the aircraft. It's going to be for a more limited controller workload, so you're only going to give commands at the waypoints. And it's going to have a more compact state space because you no longer have to represent east and north, you just represent which waypoint it's at. So the actual state space is going to be a waypoint and a speed. So on the left or the middle image, you see an aircraft flying a set of waypoints. They're going to be pieces of potential debris again, and this time they're going to be queried using the time into flight, time of launch, and time of anomaly. So each state space, we're going to run this MDP for each set of waypoints, and the state space is going to correspond with the times that are going to result in an impact between a piece of debris and a path. On the right, what we're going to see is a nominal black trajectory trying to avoid blue squares of debris. And what we actually want to do is change the distance over time, or the slope or the speed, such that the aircraft can avoid pieces of debris in time rather than in space, because you're not going to change the path of the aircraft. The action space is going to be a large or small speed up, a constant speed, or a small or large slowdown. And the reward function is going to look very similar to the heading reward function, where you have a lambda times an efficiency reward plus a safety reward. And the strength of the efficiency reward is still going to be based off of the strength of the action. And we're still looking at how close the path gets from a threshold, or how close the path gets from the piece of debris and launch vehicle. The transition function is going to increment the waypoint over time, and the speed is going to be updated using the commanded speed. We're still going to consider that the pilot responds 50% of the time. Because the time between waypoints is variable, we don't have the average pilot response rate. The time into flight is going to be incremented using the speed and distance between waypoints, and the distance between waypoints are going to follow a distribution. We don't assume that a pilot is always going to fly the straight line path between two waypoints, but realize that there'll be some noise between the points. The time of launch is not incremented because we assume that there can only be one launch per path, and the time of anomaly is updated only once. Because we're only giving reroute commands at the specific waypoints, we're giving them very infrequently. And to build in some conservativeness, we run the path for each time of anomaly that could potentially have an impact, and we run it with a 100% chance of an anomaly. So now that we have the framework, I'm going to go through a few of the solution techniques that we use. And so you need to know what we're actually solving for. So there are two things we can solve for, a value function or a policy. So the value function is going to give you a value for each state action pair. So if you're at a specific state and you take an action, what is your preference for being in that state and taking that action? So you can imagine if you're far away from a piece of debris, that your value is going to be quite high, you're happy, you're safe. But if you're really close to a piece of debris and you have to take a strong maneuver to avoid it, you're going to have a very low value. The policy is going to return the optimal action for each state. So which state had which state action pair had the highest value? So what action did that correspond to? So the first solution technique we're going to go through is backward induction value iteration. And so I'm going to walk you through a toy problem for a heading formulation, and then I'll go through and show you the algorithm. And so what you see here is a pink star, which is going to represent a piece of debris falling through your east-north grid. And the red square around it is going to represent your negative value for being in that state. So it's bad, so it's red. If we look one time step earlier, we're going to try to avoid that piece of debris. So we're just going to first look at the state directly to its left. And you have three options. We can turn left, go straight, or go right. If you go straight, you know that you're going to hit the piece of debris, so you have another red value. It's very bad. And if you turn left or turn right, there's a probability that you'll actually turn left or turn right, but there's also a probability that the pilot won't respond and you'll still land up in that unsafe region. So you become orange instead of red. And so what you're actually going to do is do this for all of the states. And what you find is the optimal actions for the states right around the piece of debris are going to be right or left. And that middle action, left and right, have the same value, so you can arbitrarily select one. And all of the other actions are going to be nil, which represents no action. You can do this again for a time step further or earlier in time. And so now you start seeing yellow actions because now you're getting safer. So they're a higher value. And this is one of the, actually, I'll wait on that for a second. So on the actual algorithm, the first place I want you to look is line 8. So line 8 is the actual Q update. So you're going to get that value function for each state action pair. And what that's going to be is the reward for that state action pair plus the sum of all of the transition probabilities of future states times their optimal value. And in normal value iteration, what you would do is cycle over all of the state action pairs a whole bunch of times until you converge on a value. But with backward induction value iteration, you use a unique ordering of the states so that we only have to cycle over them once. So in the example I just showed, we start at when the debris falls through the airspace and we moved backward in time. And by doing that, we learn all of the information about the debris so we don't have to keep cycling over it. And backward induction is really great, but it does have a few limitations. So in general, MDPs grow exponentially with their state space. And we need a solution that's computationally tractable. And so in general, this means that you have to have a coarsely discretized state space. For instance, the heading formulation that had 43 bins for your east and north location has nearly 50 million states. So what we wanted to do instead was create a solution technique that improves safety and efficiency by supporting a finer discretization and increasing computational tractability. So to do this, we decompose the problem by individual threat. So we're actually going to look at an MDP for each piece of debris. And then we're going to solve the MDP for each piece of debris using adaptive spatial discretization for backward induction, which is an algorithm that I came up with. And so after we do that, what we're going to do is re-put together all of those solutions into a single multiple threat solution. And so just like with backward induction value iteration, I'm going to walk you through the algorithm before I show it to you. So on the far left, what you see is a yellow piece of debris falling through the airspace. And that pink circle is going to be that predefined safety threshold that we have around it. The next thing we want to do is find which states in that east-north grid could potentially transition into that safety threshold. So that blue circle is going to represent all of the states that could transition into that pink circle. We take all of those states, and that's going to be the boundary for our east-north grid that we're going to solve over that and the time step before it intersects with the debris. And so what we've done here is put an 11 by 11 grid over that, and that's our state space. So then we're actually going to solve that value function. So the green circle is going to be anywhere where the value function is non-zero. So we're working with penalties, so anywhere that it's less than 0, we know something is going on. Again, for the time step before this, we need to find what our new state space will be. So we set a blue circle, which is again the reachable states, to those that could reach the green circle, and that's going to define the boundary for our next state space. We put an 11 by 11 grid into that, so we're keeping the number of bins the same, but we can see that the state space is growing. Again, we can solve for the value function, find all of the non-zero values, throw the state space around that where the states are reachable to that blue section, the green section, and set that as our next state space. So this is a toy problem, but in just 3 time steps, we can see that the state space has already grown 4 times bigger than the initial one that we used. And that's really the benefit of adaptive spatial discretization, is that we're able to focus on the regions where we're in most safety critical situations so that we can have the best, most accurate and precise rerouting commands. So the algorithm is actually going to look a lot like backward induction value iteration, but now after the Q function update, which we have in line 9, which looks exactly like line 8 of before, we're going to have a state space update, because after each sweep over a specific time, we're going to update the state space. And also at the beginning, we're going to initialize the state space based off of the pieces of debris. So now that we have our model, we have our solution techniques, we're going to have to simulate them to evaluate how they perform. So we have 2 simulation frameworks. We have a domestic simulation framework and an oceanic simulation framework. The domestic simulation framework is going to be used for the heading formulation with both backward induction value iteration and ASD, or the adaptive spatial discretization. And we're going to use 101 recorded flights. We're going to run them with various start and anomaly times. We're going to assume that during simulation, the pilot always responds, and that we're going to run over 121,000 simulations. So the image on the right is going to be those actual recorded flights, and the red dashed ellipse is going to approximate that mushroom-shaped temporary flight restriction that we saw on one of the earlier slides. So that's going to be used as our historic baseline. For the oceanic simulations, we didn't actually have data like we did for the domestic ones. So instead, what we had to do is generate some realistic paths. So we end up generating 33 realistic paths that interact with debris. And how we do this is we take all of the waypoints off of the North Atlantic route planning chart, and we randomly select a first waypoint. Then, to keep the path realistic, we randomly select a second waypoint from the neighbors of the first waypoint. We do that again for the third waypoint, but when we start adding more waypoints, what we're going to do is a smoothness check. We want to make sure that we don't have a path of an airplane flying a zigzag, which would never happen in real life. Instead, you're going to have more fluid turns or straight line paths. So we do a smoothness check. If it passes, it gets added. If not, we check more of the neighbors. If none of the neighbors pass the smoothness test, we return the path. And otherwise, we return the path after 10 waypoints are added. In the bottom right, what you see is the actual generated paths, where the light blue diamonds are going to be the starting locations, and the logarithmic histogram in the back is where potential pieces of debris are falling through the airspace. The oceanic simulations are going to be run on the metering simulations, and they're going to be run on path variance. We don't just want to run those 33 baseline paths. So instead, we assume that a pilot is always going to fly over the waypoint, and we add noise between the waypoints by sampling from a k-dimensional normal distribution. The number of simulations per path are going to be proportional to the number of path state space, the size of the path state space. So as I said in the beginning, each path has its own state space that's going to be dependent on the times of anomaly and times of launch that cause interaction between the aircraft and pieces of debris. So the sizes of the state space are also going to change. So we run these with random combinations of starting speed, time of anomaly, and times into launch. And we run over 101,000 total simulations. So now what I think is the fun part is the results. What actually comes out of this? And so the first thing we're going to talk about is the heading formulation results. And we're going to go through some of the policy results. So if you look at the image on the left, what that is going to be a frozen frame of what we're going to see on the next slide, because it's going to move over time. But this is an example policy. So you have an east-north grid, and an aircraft can be located anywhere within that grid. The aircraft we have is going to be flying from the top right to the bottom left of that box. And you're going to take one of the policies that correspond to the colors in there. So if it's white, there's no action, it can do whatever it wants. If it's gray, it's going to be a maintain action. The dark colors are the stronger actions, and the lighter colored actions are the weaker actions. And so now, if you look at it over time, you can imagine that there are potential pieces of debris falling through this portion of the airspace, and the aircraft is going to be rerouted by turning right and left around them. You'll also see that there are some gray regions that kind of expand backwards. This makes sense because a maintain action is very cheap, and it makes sure that the aircraft never flies towards the piece of debris. Again, in this formulation, we don't know where the aircraft is flying or what its future heading will be, just where it's currently located and its current heading. So in this diagram, what you see is on the top left, we have an example nominal path of an aircraft flying. In the middle one, we have the historic path that's going to fly around that red ellipse. And on the right one, you can see the proposed MDP path. And so it's much smaller than the historic one. On the bottom left, you see the actual value function values, where the darker the color, the more negative or worse it is. The middle is going to show the actual policy, and the policy is actually changing with the heading of the aircraft that it's flying. And on the right, you see where potential pieces of debris are falling through the airspace. So this way you can kind of see like a holistic view of what the MDP is considering and how its solution is reacting to the changing environment. And so what we actually did to look at the metrics is we ran this on the MDP solutions, a nominal, just the collected flight trajectory, and historic region. So we have it fly until it hits that oval and then fly around the oval. And what we did is, first of all, we did an exploration of lambda values. So we have that trade-off between safety and efficiency. And so we ran a variety of different lambda values to see which one works best with this problem and this reward function. And we ran it with different state space discretizations. So the different colors represent different east and north bin sizes. So I also have a tabulated version of these results. And so this is going to be a likelihood weighted version of the results. And we have the different state spaces. And so the numbers seem a little random, but they actually correspond to specific state space sizes. So we're looking at roughly 50 million, 75 million, and 100 million state space or size of the state space. We're going to look at the probability that an aircraft is rerouted, the average added distance, and the probability of entering that safety threshold around a piece of debris. And what our results are going to show are that in general, the finer the discretization, the safer the policy. And the policy with the largest state space has the safest policy. So it's going to be 60% safer than the nominal trajectory. And that policy also only reroutes 8% of the historically rerouted paths. We did notice that between having 43 and 53 bins, there was a little degradation of safety. And this wasn't actually a surprise because it could be due to overfitting. So you're looking at a model that's using discretization and it's multilinearly interpolating to different states. So sometimes when you're interpolating, you can actually be overly conservative at some of those states, and sometimes that can benefit your results. So we're also going to look at the metering formulation results. So on the left, you see an aircraft flying between different waypoints. And on the right, you're going to see a zoomed in version of the left. And you're going to see a black aircraft that's going to represent the nominal trajectory, and the teal aircraft that's going to be the MDP rerouted trajectory. So it's been commanded to slow down. And it's been commanded to slow down because on this path, there's going to be pieces of debris. And the black aircraft is going to hit them. And the teal aircraft is able to reroute around them. So it was very quick, and I actually kind of lagged, but I have a frozen version for you. So here you can see multiple pieces of debris actually falling through the airspace. So each blue circle, not oval, represents a piece of debris and its safety threshold around it. So the aircraft is not to scale, the circle is. And here you can see that the teal aircraft was able to safely reroute around it by going slower. Similar to the to the heading formulation solution, we also compared this solution to a few other things. So we have the proposed MDP solution, the nominal path, which is just going to be flying a constant speed path. And because we have no historic data of rerouting this way, we use a heuristic. So for this heuristic, what we're going to have is an aircraft flying between waypoints. And if an anomaly occurs, it's going to check at its current waypoint if there's going to be potential pieces of debris before the next waypoint. If there is, it's going to try different speed commands. If the different speed commands create a safe path, it's going to take them. And if not, it's going to be marked as an unsafe flight. We also looked at a lambda sweep for this so that we could make sure that our reward function was adequate for our problem. And again, we're going to have the tabulated results where we're going to look at the probability of an aircraft being rerouted and the probability that it's going to enter the safety threshold. And what we see with these results is 12.3% of the metered aircraft are safer, 12% are safer than the heuristic, and 58% are safer than the nominal trajectory. We did notice that the efficiency suffered a little bit, and there's a few reasons for this. So number one, which is a minor one, is that the heuristic only counts efficiency when it creates safety. So if its path ends up being unsafe, it doesn't mark it as being rerouted. Another one is that because of the sparse commands, the commands could potentially be over an hour apart. We've built in that there will always be an anomaly, so we're doing a lot more conservative rerouting than we potentially need to. Some of the safety results aren't exactly where we want them to be, and some of the reason for that is when an aircraft is actually interacting with a piece of debris. So the histogram on the top right is going to show you between which waypoints the aircraft's path is interacting with the debris. This is showing before the third waypoint, most aircraft are interacting with the debris. And sometimes the aircraft capabilities can't actually be rerouted around those pieces of debris. So one of the things looking forward that we want to look at is having ground holding. So you can actually hold an aircraft on the ground before it takes off so that you can actually increase the aircraft's capabilities that we don't currently have. So next, we're going to look at the single threat adaptive spatial discretization. So here we're looking at one piece of debris falling through the airspace, and you're going to notice for the next few slides, it's going to look very similar to the backward induction value iteration solution. So this is one piece of debris. On the right, you have the policy. On the left, you have the utility values. And you're going to notice that the axes are super annoying because they keep moving. But this is actually the really important part of ASD, is that the axes are moving. So on this slide, we're going to re-look at the same two plots on the top. And on the bottom, we're going to show what the axes would have to be if you were to use just backward induction value iteration. So if you took the maximum extents of the state space, what you would have to solve over. So what you see is far away from the piece of debris, ASD doesn't do that much better. But as you get closer to where the piece of debris will fall through the airspace, so when you're in a more safety critical position, you start to get a lot more focused state space, which is exactly what we want. And so we also have the results for multiple pieces of debris falling through the airspace. And what you're going to notice is if you remember the backward induction value iteration solutions, here you're going to have much more focused regions on either single pieces or clumps of pieces of debris that are falling through the airspace. And so this is just recombining all of those individual threats into a single policy. Similar to the other things, we're going to compare them against three other techniques. So we have the MDP solutions where we've again run a lambda sweep. We're going to have a nominal, so just the collected flight trajectories, and the historic rerouting around that red ellipse. And here again, we're going to look at the probability of being rerouted, the average added distance, and the probability of entering the threshold. And what we see is that using the ASD solution, we're going to be 24% safer than the nominal, and we only reroute 7.8% of the historically rerouted flights. It is important to know that the results I have for ASD and the results I have for backward induction value iteration aren't exactly a one-to-one comparison. So when you solve the solution for ASD, you have to run an MDP solution for every piece of debris. Based off of the catalog that we're using, I run over 4,000 MDPs to get that total solution. For the backward induction value iteration, you run the solution for all of the pieces of debris once, so you only run the MDP once. So for ASD, I use one debris profile for training, a different one for tuning, and a different one for testing. For backward induction value iteration, I train on 20, tune on 5, I train on 25, tune on 5, and test on 20. So the results aren't exactly one-to-one in simulation because they use different debris profiles. But if you were to compare them, the policy for ASD that has 11 bins for its east-north grid is 14% less safe than the backward induction policy that uses 61 bins for its east-north grid. So it's only a little bit less safe, and it's using a much coarser discretized state space. If you were to compare it to the backward induction value iteration results that use the same size state space, so 11 bins for east and north, it's 34% safer. And what this is showing you is that there's a lot of promise and improvement in safety that can be gained using adaptive spatial discretization. So there's definitely some room for future work. So in order for this to be an actual decision support tool, which is the end goal, is we want to make sure that we have the safety that the airlines are looking for. And so the first thing that we can do to look into this is to parse solvable and unsolvable simulations and make sure we can define the appropriate operating parameters for our system. So for instance, as I mentioned with the metering aircraft, some of the aircraft capabilities can't be used with the current metering formulation. So making sure that I find the simulations that would encourage the correct metering formulation is super important. We talk about a finer resolution in the east-north grid, but we don't talk about a finer resolution in time. So all of the heading reroutes are given in 10-second intervals, and the metering reroutes are currently given anywhere from a few minutes to over an hour apart. So how can we increase the number of aircraft reroutes we're giving to the air traffic controllers? It'd be interesting to combine the heading and metering formulations. So maybe you're metered in the oceanic area, and as soon as you hit a domestic area, you turn to heading formulations. Currently, we don't include any state uncertainty. So we assume we always know where the aircraft is and that our debris model is correct. In the future, it'd be interesting to move towards a partially observable Markov decision process, or POMDP, that includes state uncertainty. Also, to have a decision support tool, you'd need to be able to expand to all scenarios in different aircraft. So I mentioned earlier, a lot of this model is completely plug and play. So you could take out the debris profile and throw in a new one and not have to change very much at all. And so you'd want to be able to do that for all of the scenarios before you use it in real time. Finally, I think it'd be really interesting to combine offline and online techniques that you can solve the bulk of the work offline and then in real time just improve your simulation with better results. So today I was able to talk to you about my different thesis contributions, and the main ones being my MDP framework for both the heading and metering action spaces, my MDP solution techniques, including the creation of adaptive spatial discretization, and my simulation frameworks for both the domestic and oceanic flights. What this showed you was that my best case backward induction value iteration heading policy is 60% safer than the nominal trajectories while only rerouting 8% of the historically rerouted flights. My metering formulation is 12% safer than the heuristic and 58% safer than the nominal trajectories. And my ASD formulation is 24% safer than the nominal while rerouting only 7.8% of the flight. While I've been at Stanford, I've also had the opportunity to work on a few other projects. And while I didn't talk about them today, it's exciting for me to mention them. And so I got to work on collision avoidance for unmanned aircraft, specifically coordinating horizontal maneuvers. And I've also worked on neural networks for visual depth mapping.